Hey there, we're going to look at intervals of concavity and the second derivative tests in this lesson. If you are not one of my personal students, you may want to print a sheet to follow along. I gave my students a sheet with fill in the blanks to help them speed up the note-taking process, and you can access it at this bit.ly link listed right there. So let's go on and talk about concavity. With my students, we have already kind of brushed over the topic of concavity in that concave up means that a function is shaped like this. Concave down means a function is shaped like this. And we have not yet, with my students, talked about how to determine concavity. So I'm just going to give you a very quick explanation. A function is concave up when the second derivative is positive, and a function is concave down when the second derivative is negative. As we get further into concavity, we will talk about that the second derivative is really the rate of change of the first derivative, and slopes are increasing or slopes are decreasing would be a connection to concavity in a more verbal way. But there is a quick way to determine concavity. Determining the intervals of concavity is the same process as finding the intervals where a function increases and decreases. So the mechanics is almost identical. The difference is that you will be using the second derivative instead of the first derivative. So where you were finding the critical numbers, and then a lot of teachers use a number line approach to organize their intervals. You can do the same thing, but with the second derivative. And so we will start by finding what's called a hypercritical number. We will find the second derivative. We will set the second derivative equal to 0, and those values are hypercritical numbers. Also could be if f double prime of c is undefined. So pretty much the same definition as a critical number. You're just adding it, doing this with the second derivative. Do keep in mind that all critical and hypercritical numbers must actually be in the domain of the function. And so just double check that. Times that can kind of be something to think about is when you have square roots or natural log functions. If x equals c is a hypercritical number, then you have something called an inflection point if the graph of f changes concavity at that point. So if your function is concave down, and then at some point it changes its mind and decides to be concave up, that point where you transition from concave down to concave up is an inflection point. It could also be from concave up to concave down. That would be an inflection point as well. And if you have already done your full sign analysis of your second derivative, you'll see that if you are concave up, your second derivative should be positive. Concave down, your second derivative will be negative. So you can also, if you have this information, you can also find places where your second derivative changes signs, and that will be an inflection point as well. So you're looking for any change in concavity, which is when the second derivative will change signs at that hypercritical number. And so let's look at a couple of examples where we will find the intervals of concavity. The first one is a polynomial, which tends to be a little bit nicer. So for this one, we're going to go ahead and find the first and second derivatives by hand. The later ones, I have already done that for you to speed up the process. So my first derivative here is 3x squared minus 6x minus 45. My second derivative is 6x minus 6. And the first thing I want to do is get my critical numbers or hypercritical numbers. So 6x minus 6 needs to equal 0. That happens when x is equal to 1. And my personal favorite way to organize when you're finding a function to be positive or negative is to organize it on a number line. I'm going to put my single hypercritical number down here. I'll write a 0 above that to remind myself that if I were to plug in 1 to my second derivative, I do get 0 as a return. And then I pick test points, something on the right of 0, something on the left of 0, and we plug those into f double prime of x. F double prime of 0 would be 6 times 0 minus 6. That is a negative value. So if f double prime is negative at 0, it will be negative for all values left of 1. F double prime of 2 would be 6 times 2 minus 6. That is all of 6. 12 times 2 minus 6. Yeah. That is a positive value, so everything to the right of 1 will be positive. Therefore, I can now tell that my function f is concave up on the intervals negative infinity. Nope. On the interval 1 to infinity. Because on that interval, f double prime of x is positive. And then I can say that f is concave down That's beautiful penmanship. Concave down from negative infinity to 1, and that would be because f double prime is negative on that interval. So there are the intervals of concavity, and then inflection points. You're looking for any place, any hypercritical number where the second derivative changes signs. That does happen at x equals 1, and so there's an inflection point at x equals 1. And you could say because f double prime changes sign at x equals 1. And keep in mind, if you are an AP calculus student, any claim you make in any justification or explanation must be supported by work. So let me finish writing this sign, this sentence. Okay, so inflection point because f double prime changes signs. And so all of my claims here, I claimed that f double prime was positive, I claimed that f double prime was negative, and I claimed that f double prime changed signs. You have to have all of that supported without the number line. The number line does not count as written work on the AP exam. It is not read. What is my pen doing? It's not working correctly. Here we go. And so do I have supporting work if I erase my number line? And I do, because I have the place, I have the work where I found my zeros, my hypercriticals. And then I have these statements right here. F double prime of 0 is negative. F double prime of 2 is positive. There is the work that supports all of the claims that I have made so far. Okay, so let's go on to number 2. And this one's a little bit uglier. We have f of x is this thing. It's not a polynomial, but we will be using power rule to differentiate this. And let's see. So my first derivative is kind of nice. I've already pre-worked this to speed it up. So there's my first derivative. If you want to pause the video and work out the derivatives on your own, you can, and then hit play in a second. And my second derivative is right here. So the derivatives themselves, I don't think were too terrible. They're fraction-y, but you know, we should be able to handle the fractions. The difficulty comes in setting this equal to 0 and solving. And in these cases, we will factor, and they do have x's in common. They have different exponents, so we can factor out some x's. And when you factor, you always factor out the x with the smaller exponent. And so my x with the smaller exponent, writing pad is not working very well here. The smaller exponent is negative 4/3. So we will factor out an x to the negative 4/3. And to make it a little bit cleaner, I am also going to factor out a 1/9. And so right here, I have factored out a 1/9 x to the negative 4/3. And then when you factor that out, you have to remember that if you were to distribute that x to negative 4/3 back through, what do I add? It's not meant to be a 2, that's supposed to be a question mark. And then I just erase everything. What do I add to negative 4/3 to get to negative 1/3? And that ends up being 1. And so 7x to the first plus 4 is how this will factor. Now I do need to set this equal to 0, so I'm going to keep cleaning this up some. And this, I believe that's it. Yes, that is my final cleaned up version of that second derivative. I will now set that equal to 0, and we end up getting x equals negative 4/7 for something that will make that equal to 0. But you also need to be aware of any domain issues. And I have an issue down here because if I were to plug in 0 for x, my second derivative would be undefined. And so I'm also making a note that f double prime of 0 does not exist. And if my second derivative does not exist, I now am curious, does my function exist? And it does. If I plug 0 into f of 0 is 0 to the 5/3 minus 2 times 0 to the 2/3. That is 0. It is a defined point on the curve. And so that's an important thing to recognize. And so I'm going to go to my number line, f double prime of x. I have hypercriticals at negative 4/7 and 0. Boy, this is not very pretty. 0, negative 4/7. Okay, negative 4/7 actually made my second derivative equal 0. However, at x equals 0, my second derivative fails to exist. And so I'm going to put a D in E there. Now I need to pick my test points. Something left of negative 4/7, negative 1 would work. Something between 0 and negative 4/7. I don't like this, but I guess I'll go negative 1/7. Crazy fractions. Plug in 1. And we need to plug all of those test points into my second derivative. F double prime of negative 1 is 7 times negative 1 plus 4. That would be negative 3. The denominator looks ugly, however, this is the cube root of x to the fourth power. And that to the fourth power is a really nice gift, because if you raise something to an even exponent, it will always return a positive, except 0, but I'm not going to plug in 0 because I've already established that that makes my second derivative undefined. So my denominator is always going to be positive, which means f double prime of -1 is negative. F double prime of -1/7. Okay, 7 times -1/7, that's -1 plus 4 is 3 over a positive denominator. It's always positive. And then f double prime of 1 is going to be 7 times 1 plus 4. That's 11 over a positive denominator. That is also positive. And so I am going to declare that my function is concave down. On the intervals -infinity to -4/7. Concave up on the interval -4/7 to 0. And I'm going to break this up at 0 and continue after 0. Unlike intervals of increase and decrease, this is a non-existent spot. If my second derivative were equal to 0 there, if it were positive to 0, it's positive. I would probably include it to 0 to 0. That was genius. So I'm going to go 0 to infinity on this one. And then inflection points, we have one inflection point at -4/7. Whoa, inflection point at x equals -4/7, because the second derivative does change sign at that hypercritical number. So there's number 2. And then let's look at number 3 here. And this one's not too bad at first. Your first derivative. In order to do that derivative, please don't quotient rule that. Bring that x squared plus 1 to the top, make it to the -1 power, and chain rule it. It's just a whole lot more efficient. So there is my first derivative. I went ahead and multiplied the -4 times 2x, get -8x. Now the second derivative gets a little bit hairier, because now I have a product rule with a chain rule for the derivative of the second piece. If you wanted, you could move x squared plus 1 to the denominator and do a quotient rule. However, with that quotient rule, you will have a chain rule when you do the derivative of the denominator. I would rather just do the product rule. And so as I do my first pass at the derivative, here it is in its completely unsimplified version. The derivative of -8x is -8 times the second term plus -8x, and then we chain rule x squared plus 1 to the -2. I'm going to clean that up a little bit. 8x times 2 times 2x is 32x squared. The two negatives will make it positive. And now factoring this, they have an 8 in common, which I'll definitely take out. I think I'll take out a -8 because I want to make that first term a positive coefficient. And as far as the x squared minus 1 plus 1s, you will take out the one with the lower exponent, which is x squared plus 1 to the -3rd. And when you factor that x squared plus 1 to the -3rd out, you'll be left with x squared plus 1 to the +1. And I always, factoring out with negative exponents is a little bit tricky. So I will always in my head very quickly think, if I were to distribute this back through, I need to add these exponents to take me back to what I started. -3 plus 1 is -2. So I feel good about that factoring. And then after you factor out the x squared plus 1, you have x squared plus 1 minus 4x squared, which turns into 1 minus 3x squared. And then I'm going to move that x squared plus 1 back to the denominator. And I have this final version of the second derivative. I will set that equal to 0. And that gives me hypercritical numbers, and they're not very pretty, but it's x equals plus or minus the square root of 1/3. Plus or minus the square root of 1/3. You always want to be aware of a denominator with variables in it to make sure that we don't have a 0 in the denominator. However, x squared plus 1 is always positive. We don't have any issues in that denominator to worry about. It does need to be a passing thought. So now I go to my number line. This is my second derivative number line. I'm going to plot my two hypercriticals, -√1/3, the positive root of 1/3. And while that's pretty ugly, it does allow you to choose some very nice test points. 0 is right between them. 1 is after root 1/3. -1 is before root -1/3, root 1/3. And f double prime of -1 is going to be, oh my goodness, that'll be -8 times -1 squared is 1. 1 minus 3 is -2. And that denominator is always something positive. So that will return a positive value. F double prime of 0 is -8 times 1. That's -8 over something positive. That will return a negative. And then f double prime of +1 is going to end up being the same as f double prime of a -1, which is -8 times -2 over something positive. That is something positive. And finally, I can answer our question. We are concave up. Left of -√1/3 and after the square root of 1/3. And then we're concave down. Come on, pen. Concave down between those two hypercriticals, between -√1/3 and +√1/3. And then we have an inflection point. We actually have two. When the second derivative changes signs, that happens at x equals -√1/3 and +√1/3. So there are a few examples of finding your intervals of concavity and finding inflection points. The last thing I want to talk about, and man, this is a long video. Last thing I want to talk about is the second derivative test. Now, the name of this is a little bit confusing because when I ask students, what does the second derivative test do? They usually say it finds concavity, and it doesn't. The second derivative test does not find concavity. It uses concavity, but it's used to determine if a critical number is a local extrema. The same thing that the first derivative test finds. The first derivative test uses intervals of increase and decrease to find a local extrema. Concavity, the second derivative test makes the same determination, except the second derivative test uses concavity to find out whether your critical number is a max or a min. So let's talk about the mechanics of this. A local maximum. First, local extrema always occur at critical numbers, not hypers, critical numbers. So find your critical numbers, and let's say C is a critical number of F. So if C is a critical number of F and your second derivative is negative, then your graph has a local maximum. So let's think about that combination. A critical number means your derivative is 0 or undefined. And in this case, most of the time, it's going to be when the derivative is 0. And so if f double prime of C, if f prime of C is 0, that means my function is temporarily horizontal. We have a horizontal tangent. If we are concave down at the same time, if we are concave down while we have a horizontal tangent, we are talking about the top of the mountain. It is the point that is at the maximum. So the local maximum and then a local minimum. If you have a critical number and you find out that your second derivative is positive, well, if your second derivative is positive, that means your function is concave up. And if you're looking at the point where your slope is 0, you're looking at the bottom of that mountain, bottom of the mountain, bottom of the valley, that is a local minimum. And then, unfortunately, the second derivative test does have an inconclusive situation, and that is if the second derivative is equal to 0. And in that case, you would go back and you'll try the first derivative test because there is not an inconclusive portion of the first derivative test. So let's do one example. This is a second derivative test to find all local extrema for f of x equals this. And the first thing we would need to do is find the derivative and set the derivative equal to 0. If you're looking for maxes or mins, you should initially think critical numbers. So let's get those critical numbers. Let's factor out a 3. That gives me what? X minus 2, x squared minus 2x minus 15. And that will factor to x plus 3x minus 5. Set that equal to 0, and we have critical numbers of -3 and 5. And here's the beauty of the second derivative test. When it works, it's very efficient. I don't have to do a number line. I don't have to test all these intervals. I'm going to find my second derivative, which is 6x minus 6. And then I'm going to see the concavity at those points. So f double prime of -3 is 6 times -3 minus 6. That's -24. That is less than 0. That means my function is concave down at a point where the slope was 0, this is a local maximum. Local max at x equals -3. And then we're going to do the same thing. We're going to test x equals 5. F double prime of 5, 6 times 5 minus 6. That's 30 minus 6 is positive 24. That is a positive value. If your second derivative is positive, you're concave up. If you're concave up at the same time while your slope is 0, then you're at the bottom of that valley. That is a horizontal tangent. You're looking at a local minimum. Therefore, local minimum at x equals positive 5. And that is it. I did have one other example that I wanted to try, and you can read that and try it if you want to very quickly, but this has gone on long enough. I don't like my videos to get longer than 15 minutes, and I'm still rambling, so we're done.